solve this question. As you can see, in both cases, we need just to know the electric field due to a uniformly charged distribution, right? We only need that. So let's figure it out. So if I have this system, let me just copy this system. What is the electric field at a distance r? And let me just make an r here, a vector r. What is the electric field? You need a Gauss surface there, right? And inside this Gauss surface, E times 4 pi r squared is rho times 4 pi r cubed over 3 divided by epsilon 0. So the magnitude of E is rho times r over 3 epsilon 0. The magnitude is this, right? But notice that the electric field is also aligned with the r vector. R vector is pointing there. Did I just say magnetic field? I didn't, right? Maybe I might say magnetic field, electric field. Okay. Did I say it? Magnitude, yes, that's why I was. So the magnitude of electric field is this one, but it's also aligned with the radius vector. So the electric field is rho times r vector over 3 epsilon 0. And it's a general thing. Okay? So for any point in space, for uniformly charged distribution, E is rho r vector divided by 3 epsilon 0. Very good. We can actually use that. So if this is the 0 of the coordinate, we can actually transfer that knowledge to this other situation. So over here, I have a vector B pointing to the center of this object. Okay. And then let me say that this is a distance, a vector r. Okay. I hope you will not be lost with this thing that I'm going to do. Is this vector r minus b? Yes? So is this charge density negative rho? Yes? So I'm going to use the same formula for the negative charge as well. So the electric field for that one is negative rho times r minus b over 3 epsilon 0. Do you see? So if I did the superposition, so let me just bring them together. E total of this system, including the void, is rho r over 3 epsilon 0 minus rho times r minus b over 3 epsilon 0. So E total is rho times b over 3 epsilon 0. A beautiful application of vector algebra leads us to this beautiful result. This is a very intriguing result. It tells you that inside this void, the electric field is uniform. Remember, B is just a vector pointing at the center of this void. So it tells you that inside this, the electric field just points in the same direction as the vector between the centers of these two spheres, and it has a constant magnitude. It's rho b over 3 epsilon 0, pointing in the same direction. So next time you want to create a uniform electric field, you might consider getting a large sphere and putting a void inside it. Okay? Or just using a capacitor.
These spheres are, what is the made of? I mean, they are conductors?
Yeah, very good question. So since I'm saying that the charge is distributed everywhere, must be an insulator. Okay? Very good. Let me continue with a new chapter. Okay? Chapter 23, electric potential. So let me start with a concept called conservative forces. Let me just use this color, conservative forces. Indeed, every force that we do know is conservative, except for friction, but it turns out friction is just a manifestation of our ignorance, and it's a long story. But conservative forces, example, gravity. Gravity is a good example. So what I'm trying to say here is that, let's say I have a mass like this. When I take this mass up here on a certain path and take it down here on a different path, the total work that I'm doing is 0. Okay? You might be thinking that when I take it up and bring it down, I don't get the total energy of 0. I always get more tired even when I'm pulling it down. But that's just your biology, and you have to, yes.
The problem with your example is that it has a liquid inside.
No. Just even this. Yeah. I get more and more tired, but it's for a different reason, because to sustain the force, you see, when I'm taking it up, I'm applying force in this direction, okay? When I'm putting it down, I'm applying a force in still that direction, right? So when it goes up, it's positive work. When it goes down, my force is still up, because otherwise it would fall. It's negative work.
Because you want to sustain an arbitrary velocity.
Yeah. Like even if I'm doing it adiabatically, very, very slowly, and we have to assume that I'm doing that. I don't want to take too much of your time, because you must have heard these things in Physics 101, right? So whenever you have a conservative force, you can talk about potential energy. Whenever you don't have a conservative force, which is in principle never, but if you are dealing with a friction, with a system that has a friction in it, then you can't really talk about potential energy in the same way. But let's see what is potential energy. So let's go back to our example of going from A to B in gravitational field. Okay, gravity points in this direction, right? There is a mass here that I'm going to take up a height h. So I'm pushing with a force F. When I go from A to B, work done to take it from A to B is force times the distance, right? So force must be equal to the gravitational force. So this is the work I'm doing on the system. Do you agree? Any questions up to here? This work done is equal to negative of the change of the potential energy of the system. So UA minus UB. UA minus UB is mgh, not mgh, negative mgh. Right? In other words, UB minus UA is mgh. So the point B has mgh larger potential energy than point A. Do you have any questions at this point? Yes.
I think in the first line we also have a minus sign.
In the first line, we also have?
A minus sign in your last question.
No, it's, you mean this one, right? Yes? So this is the F that we are applying. Mg is due to the gravity. Right? So this is the work that we are doing on the system. F times the distance, and we are moving in this direction, so they are aligned. So it's mgh. Okay? Maybe, so notice that yeah, you are right. There is some minus sign missing here. I'm missing some minus sign there. I will fix it. Don't worry about it. You know what the potential energy is, right? Should I be worried about this? mgh minus delta U, UB minus UA. So I wrote it as UA minus UB.
So which way you define positive?
Okay, let me erase this part. There you go. UB minus UA is equal to mgh. I keep doing these negative errors. So let's fix it when we deal with this electric potential energy part. Electric potential energy in a uniform field, electric field. So to create a uniform electric field, I'm going to assume that I have a plus charge over here and a minus charge downstairs here. So there's a uniform electric field pointing in this direction. Okay? So I'm going to take my charge, let me just put it here, from point A to point B, and it's a positive charge. It's a positive charge. So where does the positive charge wants to move?
In the direction of electric field.
In the same direction, right? So just whenever you are not sure about what's going on with the potential energy, just remember this. If it's going where it wants to go, the potential energy difference will be negative. If it is going to where it doesn't want to go, the potential energy difference will be positive. It's like taking something uphill, it doesn't want to go there, so the potential energy difference is plus. Taking something downhill, it actually wants to go there, potential energy difference is negative. By potential energy difference, I mean final minus initial. Okay? So over here, we took it up. Did it want to go there?
No.
So the potential energy difference is positive. Final minus initial. Okay? I found my mistake. My mistake was the following. Work done on the system is equal to delta U. It's not minus delta U. Work done by the system is minus delta U. Okay? That was my mistake. Sorry. So, we do a work on the system. You see, over here we can say that work done by the system is negative delta U, right? Do you understand this? So what is the work done by the system? If this is the electric field, this is plus Q, and let's say this is the distance of D. Then the work done by the system is Q times E times D. And that must be negative delta U. So UB minus UA is negative QED. Does everyone understand this? Final potential energy minus initial potential energy is negative because the charge wants to go that way anyways. Okay? So we have a decrease in potential energy. Any questions? So let's talk about electric potential energy of point charges. Okay, two or more point charges. What happens if you put together several charges and ask what is the potential energy? Now, to do this, let's start with one of the charges. Let's say I have Q1 here, and at a distance r, I'm going to put the Q2, but I'm going to bring that Q2 from infinity. Okay?
John,
Yes.
before that, may I ask a question?
Sure, of course.
So we calculate the potential energy and we base just the electric potential energy. But I'm confused that here, isn't it there also gravitational energy?
Yes,
Why
very good
we
question.
don't count that?
Very good question. Usually when you compare electrostatic effects and gravitational effects, usually electrostatic is 10 to the 20 times more effective. So even if we put it like this, but of course, for example, in famous Millikan's experiment of oil drop, gravity is important. But if you have just a charge by itself, you remember in the oil drop experiment, it's the whole oil drop of 10 to the 23 atoms, right? And then you put one electron in it, and it can hold it up in the air. But if it's just one electron, doesn't really matter. You see? Yes? Okay, very good question. Now, plus Q is going to be brought from infinity, and we have to assume something. We have to have a reference point. When plus Q is at infinity, we call that situation to be 0 potential energy. Then we bring this over here. Now plus Q2 is here. How much work have we done? Let's find it out. Do you have any questions, problems here? Sometimes I will look at work done on the system, sometimes work done by the system. Do you have any problems with that? No. Okay. So in this case, let me go from this final situation to the initial situation because it's easier to think that way. So in the final situation, I am at a distance r, and I'm going to take it to a distance x, let's say, at a distance x. What is the force acting on this second charge? At a distance x. You know this. Please answer. K Q1 Q2 over x squared. Let's take the integral f dot dx, okay, and let's go from r to infinity. By doing this integral, are we going to find
The work done by the system.
the work done on the system or by the system? By the system. Do you agree with that? Yes. What is the difference? So let's say I'm taking this up, and the system in this case is gravitational field. Okay, I'm doing work against gravity. Okay, when I'm doing this, gravity is doing negative work, I'm doing positive work. When I'm doing this, I'm doing negative work, gravity is doing positive work. Okay, whoever wins is doing positive work. Okay, tell me, you had a question.
The work you've done is on the system, but the work
Done by the gravity is done by the gravity, done by the system. In the case of electrostatics, when charges repel each other and go away, let's say, then the work is doing work. The system is doing work. When I'm considering what I am doing there, I'm doing negative work because I'm not letting it not happen. Did you get? Yes. All right. So work done by the system is this, and let's take this integral k q1 q2 integral 1 over x squared going from r to infinity dx. What is this integral?
Minus 1 over x.
1 is 1 over x, so I get minus k q1 q2 1 over x evaluated at infinity and r, right? Which gives me minus k q1 q2 1 over infinity minus 1 over r, which is k q1 q2 over r. This is work done by the system if it goes from UB to UA. Work done by the system should be negative of change in the potential energy, right? What is the change in the potential energy? UA minus UB. is negative of this. So UB minus UA is positive of this. Okay? And since we called this one 0, UB is simply called K, Q1, Q2 over R. Let me just... Okay? So, any questions related to these ideas? Comments, questions? Did you get it? You know this from high school, right? When you have two charges, that's the potential energy. I might say sometimes potential and forget that I'm supposed to say potential energy. Please excuse me for that if I'm doing that. But there's a difference between electric potential and electric potential energy. You either don't know it and you are about to learn, or you do know it, so there's no problem. So, let me just here also draw it. So whenever you have a system like this, this is how you get the potential energy of the system. For example, let's say I have two electrons sitting like this at a distance r. And they have a mass of me. What is going to happen when I release them? Both of them are electrons. They will repel, right? So they will fly to infinity. My question is, what are their velocities at infinity? Do you understand the question? Yes?
Since we defined the potential energy to be 0 at infinity, all the potential energy will be conserved into kinetic energy. And that since they have equal masses, by momentum, the kinetic energy will be shared equally between them. So you can solve it.
Yes. So at infinity, both of them will go with the same velocity in opposite directions, right? And at infinity, the U infinity will be 0, right? So all the potential energy will turn into kinetic energy, and kinetic energy is going to be me v infinity squared over 2 times 2, right? And how about the potential energy? At infinity it's 0, yes, let me just write it like that. So kinetic plus potential is like this, and at the beginning there is no kinetic energy, but all of them is potential energy. And what is the potential energy at the beginning? Ke squared over r. Everybody agrees with this? Yes? So what do we get? Me v infinity squared equals Ke squared over r. V infinity is equal to Ke squared over r mer square root. Okay? Nice application of potential energy.
Size biraz daha bunun güzeli bir soru sorabilir miyim?
Yes?
We could also think this as like there is this one lead nucleus and one, alpha particle. Since lead nucleus is so much heavier than the alpha particle, we assume that lead nucleus remains, fixed. So the alpha nucleus approaches with velocity. It has a kinetic energy. And if it is approaching it in a direct line, it will just approach it the distance and start repelling, in the opposite direction. But if it has a non-zero angular momentum,
Yes.
what happens then? I mean, I solved this, but maybe if you could solve it again in class, it would be what? Kapı açıcı.
Okay, but let me solve an easier question, because otherwise you might
There's
get the
a
idea that
momentum, it gets really good.
I see. But we ask much simpler questions in the exam. So let me solve that kind of a question. So for example, yes,
May I ask a general question? Like for the infinity potential energy, can we say it is maximum?
can you say it is like 123? Yes. But then your result will be 123 plus ke squared over r. You see?
It is like we are not interested in the potential, we are interested in the potential difference.
Exactly. Not in the potential energy as a value itself, but if you look closely, we are always dealing with potential energy difference. Now, I will ask the similar kind of question, but just to show you what to do when you have multiple objects. So the same question, this is A, this is minus E. So this time I have 4 electrons. All right? Arranged on a square. What is the velocity at infinity? I'm asking this just for the purpose of calculating the potential energy at the beginning. So how would you calculate potential energy for this particular system? Yes, again?
Well, we need to calculate each of
Mm-hmm.
particles, like each of the pairs.
Each of the pairs, that's a better version of saying it. So each of the pairs, how many pairs do we have? 1, 2, 3, 4,
6.
5, 6, right? This one's as well. So for these 4 pairs, I have 4 times ke squared over a, right? And for this ones, I have a square root 2, right? So I have plus 2 of ke squared over a square root 2. And this whole thing should be equal to 4 times me times v infinity squared over 2. That's it. You can find the answer later on.
Will we do the quiz?
Hmm?
Will we do the quiz?
We will do the quiz in 5 minutes, if it's okay. Yes? Let me just mention to you electric potential. It doesn't have energy in it. Just electric potential. Okay? So, just as we defined electric field as force divided by charge, test charge, here we are going to define something called potential, and it is basically potential energy divided by charge. Okay? So potential energy has a unit of joules. This one has a unit of coulomb. Joule per coulomb is called volt. Okay? 1 volt is 1 joule over 1 coulomb. So far, so good? Yes? Now, for example, let me have plus q over here, plus q1, and there is a distance of RA here, and I have a point A there, and another one at B. This is RB. The question is, what is VA minus VB? How would you find VA minus VB? So this Q is the test charge. Okay, what you do is you imagine a test charge and you place it at A, like plus Q being at A and plus Q being at B. And then you say that VA minus VB is simply UA minus UB divided by Q. Does it make sense? So what is UA? K, Q, Q1 over RA, right? What is UB? K, Q, Q1 over RB. So VA minus VB is K, Q, Q1 over Q, right? Because you have to divide it by Q, times 1 over RA minus 1 over RB. So VA minus VB is K, Q1, 1 over RA minus 1 over RB. Okay? Any questions? Yes? No? No questions? Do you want to have a quiz?